The six trigonometric functions are of central importance in the study of trigonometry, and they arise from the ratios of the sides of right triangles. So let's consider a right triangle here. Now, we're familiar with the fact that the right triangle has one interior angle with a measure of 90 degrees, or pi over 2 radians, and then it has two acute interior angles. Now, if I specify one of these angles and label it, say, theta, then I can look at the various sides of this triangle, and I could maybe label their lengths, A, B, C, like this. Now, the important thing to note here is that if I were to construct another triangle, which is larger but has the same angle measurement in the acute angle theta here, then these two triangles are similar. And even though these side lengths, A prime, B prime, and C prime, will be different than the side lengths of the first triangle over here, what we do have is a relationship between their ratios. So, by similarity of triangles, we have that corresponding ratios are equal when we look at the lengths of sides for the two triangles. So for instance, we have that A over B is equal to A prime over B prime. And we have that A over C is equal to A prime over C prime, B over C is equal to B prime over C prime, and so forth and so on. We've got these various ratios that we can take. The point is that the ratio of the sides, the corresponding sides A to B, A to C, or B to C, doesn't depend on the size of the triangle, only on theta. What this means is that we can define a function, or really we're going to define 6 functions, that take as an input the angle theta and give as an output the ratio of sides of a right triangle with one of the acute angles being theta. And because we have this similarity of triangles which says that these ratios are equal, this function will be well defined. It won't depend on which triangle we're looking at with that angle inside, because they will all have the same ratios. So from this we can get to the definition. So we're going to be building up the definitions of the 6 trigonometric functions in pieces, and the first place we're going to start is with sides of a triangle, as I just mentioned. So given an acute angle theta and any triangle, any right triangle, with theta as an interior angle, we define 6 trigonometric functions. And I'm going to do this by making reference to a picture of the sort of triangle that I'm talking about. So over here, I'm going to take any triangle, which is a right triangle, and has one interior angle with measure theta. And what I'm going to do is I'm going to identify the 3 sides of this triangle using terms in with regards to this angle. So for instance, I'm going to label this side OPP for opposite. the side of the triangle which isn't adjacent to the angle theta is called the side opposite theta. The side of the triangle which isn't the longest one but is adjacent to theta is called the adjacent side, or ADJ. And then the longest side of the triangle, which is opposite the right angle, is HYP for hypotenuse. So we've got opposite, adjacent, and hypotenuse. And given a triangle like this, I can look at the ratios of the sides of this triangle. And as mentioned previously, those ratios only depend on theta, not on the specific size of triangle that I'm dealing with. So, for instance, we're going to define one function which is sine. Sine of theta, denoted sin, theta, is going to be the ratio of the opposite side of the triangle over the hypotenuse. So sine is opposite over hypotenuse. Cosine of theta will be adjacent over hypotenuse. We'll do some examples with this very quickly. We'll also have tangent of theta, which is opposite over adjacent. Now let me write down what these are below. So SIN stands for sine, S-I-N-E. Cosine, spelled like this, and tangent is described this way. And so these are the three most familiar trigonometric functions, but we also have three others that we get by taking the reciprocals of these ones. So we have secant theta, which is hypotenuse over adjacent. We have cosecant, CSC theta, which is the hypotenuse over the opposite. And we have the cotangent, COT, which is the adjacent over the opposite. And so this is pronounced cotangent. And so given any angle theta, any triangle, we can identify one of the sides, one of the angles rather of the triangle, and define sine, cosine, tangent, cosecant, secant, and cotangent of that angle. So for the sake of example, let's suppose that the opposite side was 3, the adjacent side was 4, and the hypotenuse was 5. This is actually a right triangle. So in this example, for this angle, which I haven't specified, it's actually not a super familiar angle here, but whatever this angle is, the sine of that angle will be 3 over 5. It's the length of the opposite side divided by the length of the hypotenuse. Cosine of this angle is going to be the length of the adjacent side over the length of the hypotenuse, so 4 over 5. Tangent of theta is going to be equal to the length of the opposite side over the length of the adjacent side. Secant of theta, secant is hypotenuse over adjacent, so that'll be 5 over 4. Cosecant of theta is hypotenuse over opposite, so that's 5 over 3. And cotangent of theta is equal to adjacent over opposite. So that's 4 over 3. So given a triangle with various sides to it, if you know the sides, then you can identify the sine, cosine, tangent, cosecant, secant, and cotangent of each of those angles. So this is the basic idea here, and these sines, cosines, tangents can be approximated in a calculator when you know the angle, or when you don't know the angle. If you can work out the lengths of sides of the triangle, you can still work out what their values are when you plug them into the 6 trigonometric functions. So let's first think about how we remember how this goes. So the first thing to notice is that the 3 functions on the right in my table up here are the reciprocals of the ones on the left. This is very important for remembering how they go. So notice that cosecant, which is hypotenuse over opposite, and sine, which is opposite over hypotenuse, are reciprocals of each other. So that means that cosecant of theta is actually the same as 1 over sine of theta. It's the reciprocal. And secant is 1 over cosine. Cotangent is 1 over tangent of theta. And you'll notice that I've been inconsistent with whether I put parentheses around the theta or not. We'll often drop them for the sake of more efficient notation. So what the reciprocal identities here tell us is that if we remember that cosecant matches up with sine, secant matches up with cosine, and cotangent matches up with tangent, then we just need to remember what the ratios are that define sine, cosine, and tangent. So for this, there are several mnemonics that you can use if it's helpful. The most common of which, the most well-known, is the so-called Socatoa. And there are various mnemonics for remembering this exact sequence of syllables, but most people find that they just use Socatoa and memorize them. And what this stands for is that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is equal to opposite over adjacent. So if we can remember these and remember that each of the other 3 functions is just the reciprocal of one of these, then we can work it all out. So let's take an example. So let's let theta be the angle in the following triangle. Now I'm going to specify, of course, which angle is referred to by theta because there are a couple of them. So let's make theta this angle down here. And let's suppose that we know that this side has length 2, and let's say we know that the hypotenuse has length 5. But that's all the information that's given to us, other than this being a right triangle, of course. And the problem is to find the values of the 6 trigonometric functions at theta. So we want to find sine of theta, cosine of theta, tangent of theta, secant, cosecant, and cotangent of theta. So one of them we can find pretty easily. Sine of theta is, by our mnemonic, sine is opposite over hypotenuse. So we look at this angle and we say, all right, what's the opposite side to that? Well, that's the side with length labeled 2. The opposite side is the one that isn't one of the two sides of the angle theta. So sine of theta is going to be the length of the opposite side divided by the length of the hypotenuse. So sine of this angle is 2 over 5, or 2/5. From this, we can actually figure out immediately what the cosecant of theta is. And that's because cosecant is the reciprocal of sine. So cosecant is hypotenuse over opposite, whereas sine is opposite over hypotenuse. So since the sine of theta is 2/5, cosecant of theta will be the reciprocal of that, namely 5/2. Now what about cosine theta? Cosine of theta would be the length of the adjacent side divided by the length of the hypotenuse. Now we know the length of the hypotenuse is 5, but we actually don't have the length of the adjacent side labeled. Here's where we can use the Pythagorean theorem. So the Pythagorean theorem, which is possibly the most famous theorem in all of mathematics, says, as you know, that if I have a right triangle with side lengths A, B, and C, the Pythagorean theorem says that a squared plus b squared equals c squared. If I take the lengths of the two legs of the triangle, square them, and add them, I get the square of the length of the hypotenuse. So we want to figure out what the length of the adjacent side of this triangle in the problem is. One way we can do that is by giving it a name and then using the Pythagorean theorem. So for us, the Pythagorean theorem says, for our triangle, that 2 squared plus b squared is equal to 5 squared. Well, this we can work out. 2 squared is 4, 5 squared is 25, so we get that b squared is equal to 21 after subtracting 4 from both sides. And so b would be equal to plus or minus the square root of 21. Now, a negative value of b doesn't make sense in the context of this triangle, though it will have an interpretation a little bit later once we start looking at angles that are not acute. So for us, b will be equal to just the square root of 21. And so one thing that you'll notice as you start doing problems is that a lot of times, a lot of triangles you deal with have side lengths that are square roots of something or other. This is not a problem. In fact, this is very expected. Triangles where all of the side lengths are integers are really rather rare. And so most of the time we'll be dealing with triangles where at least one of the sides is a square root of something or other. So in this problem, cosine of theta is equal to the length of the adjacent side, which is the square root of 21, over the length of the hypotenuse, which is 5. Once we have cosine, we can work out secant, because secant is the reciprocal of cosine. the secant of theta will be the reciprocal of the cosine of theta. Cosine of theta is the square root of 21 over 5. Therefore, secant of theta is 5 over the square root of 21. Finally, we want to get tangent of theta. Tangent is opposite over adjacent. The opposite side is 2. The adjacent side has length square root 21. We worked that out already. And cotangent of theta is the reciprocal of tangent. So it's the square root of 21 over 2. So this is a basic example for how we can take a right triangle. As long as we know 2 of the sides, we can figure out all of the trigonometric functions of one of the angles. We may have to use the Pythagorean theorem in order to do that, but we can. A slightly different but similar type of problem is the following. If theta is an acute angle and sine of theta is equal to 7/8, find, let's just say, cosine of theta and tangent of theta. So in this case, we aren't given a triangle to work with, just an angle. But here's where we can take advantage of the similarity that we talked about, that we've been talking about the whole time. When you're just given an angle, we can construct any triangle we want that has the properties given. In this case, where sine of theta is 7/8. So for this kind of problem, we can construct any triangle we like with sine of theta equals 7/8. So we can go ahead and construct a triangle here. We'll leave theta on this side. And now we know that sine is equal to opposite over hypotenuse. So what we need is for the opposite divided by the hypotenuse to equal 7/8. Now there are actually lots of ways for us to do this. Let me write down a few possible ways that we could do this. We could make the opposite side have length 7/8 and the hypotenuse have length 1. This triangle that we've written down, where we haven't worked out what the adjacent side is yet, has a sine value of 7/8, or sine of this angle theta has a value of 7/8, because sine of theta in this case would be 7/8 divided by 1, which we know is 7/8. On the other hand, we could do something like 14 and 16. Now sine of theta would equal 14 over 16, which is 7/8. And so this triangle will work also. This triangle will also work to determine what cosine of theta and tangent of theta are. But the best way to do it is to exactly match up the numerator given with the hypotenuse given. And so the best thing to do here really is just to put the 7 in the opposite side, the 8 on the hypotenuse. Any one of these triangles will work, but doing it this way, where we just take the numerator and denominator, make them the lengths of the opposite side and the hypotenuse, is the easiest way to do it. And easy ways of doing things are what we like. So once again, we're going to need to figure out what this adjacent side down here is, and we can use the Pythagorean theorem. we have that 7 squared plus b squared is equal to 8 squared. So 49 plus b squared is equal to 64. And so b squared is equal to, subtracting 49 from both sides, we get 15. So b will be equal to the square root of 15. Therefore, we can figure out exactly what cosine and tangent are. So now, cosine of theta is the adjacent side, which has length square root 15, over the hypotenuse, which has length 8. And tangent of theta has length, the length of the opposite side, which is 7, divided by the length of the adjacent side, which is square root of 15. And so this is how we can use the value of one trigonometric function to find the values of all the rest, as long as you know that you're starting with an acute angle, theta. Little point here, a lot of times you will see in textbooks or other places where you can learn trigonometry that we would want to what's called rationalize the denominator, which means to get a different form of this answer 7 over square root of 15 that doesn't have a square root in the denominator. However, this is fairly old-fashioned and there's not any good reason to do it anymore, nearly ever. So we're not going to worry about this. Square roots and denominators are perfectly fine, unless we're trying to do something very specific, in which case we'll adjust. But nearly always leaving your denominator as square root of something is just fine. There are a few acute angles which are particularly important to us, and they are the acute angles of 30 degrees, 45 degrees, and 60 degrees. So let's look at our special angles. 30 degrees, 45 degrees, 60 degrees. We're going to want to know, or at least be able to find, the values of sine, cosine, tangent, etc. for all of these angles very quickly. And the way that we're going to do that is by having reference triangles. We're going to have standard reference triangles that we memorize that involve angle measures of 30 degrees, 60 degrees, and 45 degrees. So let's start with 30 degrees, 60 degrees, and 30 degrees and 60 degrees. So to do this, I'm going to start with an equilateral triangle. Now this isn't a right triangle, but we're going to construct a right triangle out of it. So remember that when we have an equilateral triangle, all of the angles inside are 60 degrees. And this is because in an equilateral triangle, all the angles inside are equal, as well as the side lengths all being equal. And so since the interior angles of a triangle have to add up to 180 degrees, the three interior angles of an equilateral triangle each have to be 60 degrees. Now, for reasons that will become apparent in a second, I want to consider specifically an equilateral triangle with side length 2 on each side. Next, in order to get an equilateral triangle, I'm going to cut it in half this way. And because I did this by hand, it's not exactly perfectly balanced here, but that's okay. Now, if I cut things in half here, notice a few things happen. First of all, this angle here becomes 30 degrees. And this angle here is also 30 degrees. And furthermore, the length of this side here is 1. for both of these smaller triangles. So what I've done is I've taken an equilateral triangle and I've split it into two congruent right triangles where I know that the angles inside are 60 degrees and 30 degrees. So what I want to do now is to just copy one of these triangles down and look at it a little bit more closely. And I'll go ahead and copy it down in approximately the same orientation that it was, but I'm going to scale it up a bit for us to look at. So we've got a right triangle here with interior angles of 30 degrees and 60 degrees. Its hypotenuse has length 2 and one of its sides has length 1. We want to figure out what the other side is so that we can work out all of the trigonometric functions that we want. So by the Pythagorean theorem, we have that 2 squared plus a squared, 2 squared, the hypotenuse squared, equals a squared plus 1 squared. So that means that 4 is equal to a squared plus 1. So 3 is equal to a squared. So a is equal to plus or minus the square root of 3. But of course, we're just looking at side length of a triangle, so a negative doesn't make sense here. So our other side is square root of 3. And this is the triangle that you want to memorize. It has side lengths of 1, 2, square root of 3, and that's how I like to run through it in my mind because it's easy to remember that way. 1, 2, 3, except the 3 has a square root on it. Now, to remember the way that all of these angles are set up, remember that when you have a small angle, that has to be opposite a small side. So the 30-degree angle is a small angle. It's smaller than the 60 degrees over here, and so it has to be opposite the smaller side, the smaller leg of the triangle. 60 degrees is larger, and so it has to be opposite the larger side of the triangle, and square root of 3 is greater than 1. And finally, 2 is the hypotenuse. That has to be the longest side. The hypotenuse is always the longest side of a right triangle, and 2 is more than the square root of 3. The square root of 3 is approximately 1.7. And so 2 is the hypotenuse. It's on the longest side. 1 is the smallest side, so it's opposite the small angle of 30 degrees. And then the middle angle of 60 degrees is opposite the middle length side of square root of 3. So this is the standard reference triangle that we want. And sometimes we'll write it like this. A lot of times I will sketch it out sort of with a horizontal alignment. A lot of times that sits better on my page. So the small angle is 30 degrees, the large angle is 60 degrees, and I know my side lengths are 1, 2, and square root of 3. I know that the smallest side, 1, has to sit opposite the 30-degree angle. I know my hypotenuse is 2, because that's the largest of my 3 numbers, and then the remaining side has length square root of 3. So here's our standard reference triangle for 30 degrees and 60 degrees. We call this our 30, 60, 90 triangle. All right, now that we have this, we can work out all the trigonometric functions for 30 degrees and 60 degrees. So sine of 30 degrees is the opposite side over the adjacent. And now notice, because we're looking at sine of 30 degrees is the angle we're looking at when we're determining, all right, what's opposite, what's adjacent, so forth. So if we look at the 30-degree angle, the opposite side to that has length 1 in our triangle. And the hypotenuse has length 2. So sine of 30 degrees is exactly 1/2. Cosine of 30 degrees is the length of the adjacent side. And again, which side is adjacent depends on which angle you're looking at. In this case, we're looking at our angle of 30 degrees. And so the adjacent side has length square root of 3, and the hypotenuse still has length 2. So cosine of 30 degrees has length square root of 3 over 2. Tangent of 30 degrees is the length of the opposite side over the length of the adjacent side, and once again, that depends on the angle that we're looking at. So sine of 30 degrees is 1/2, cosine of 30 degrees is square root of 3 over 2, tangent of 30 degrees is 1 over square root of 3. And then we can work out the other three trigonometric functions from here as well, just by taking reciprocals. So for instance, cosecant of 30 degrees is 2, because it's the reciprocal of sine. Secant of 30 degrees is 2 over the square root of 3, because it's the reciprocal of cosine. And cotangent of 30 degrees is square root of 3, because it's the reciprocal of tangent. So now let's get the values for 60 degrees. Let's see, sine of 60 degrees is equal to the square root of 3 over 2, because now the opposite side is the side opposite the 60 degree angle, and the side opposite the 60 degree angle has length square root of 3. Cosine 60 degrees has a value of 1 over 2, because the adjacent side to the 60 degree angle has length 1, and the hypotenuse has length 2. And then tangent of 60 degrees has value opposite over adjacent. The opposite side is square root of 3, and the adjacent side has length 1. So tangent of 60 degrees is square root of 3 over 1, which we usually just write as square root of 3, of course. So these are the values that you need to be able to find quickly for the angles of 30 degrees and 60 degrees. Now, I don't memorize sine of 30 degrees, cosine of 30 degrees, tangent of 30 degrees, and all the rest for 60 degrees also. I memorize one thing. I memorize the triangle. And the triangle allows me to determine what any trigonometric function of 30 degrees or 60 degrees are, as long as I label everything properly. So don't focus on memorizing that sine of 30 degrees is 1/2. Focus on memorizing the triangle, which encodes all that information and tells you 6 different trigonometric functions of 30 degrees and 6 different trigonometric functions of 60 degrees. It encodes a whole lot of information much more efficiently than just memorizing a collection of values. And it's going to be much more useful to us as we move forward in the course as well. So memorize the triangle, not the values of the functions themselves. Okay, so that handles 30 degrees and 60 degrees. Let's talk about 45 degrees. Now, to get the 45 degree angles, we're going to do a similar thing where we cut a figure in 2 pieces, but in this case, the figure I'm going to work with is a square. So I want to start here with a square with side lengths 1 on all sides, and with all of the angles inside being 90 degrees. And now I want to cut it corner to corner, like this. And when I do that, notice that I've cut the square into 2 congruent right triangles, and the 90-degree angle that's been split by the green line has a measure of 45 degrees, because that's half of 90. So that means that we can get a triangle. Again, I'll bring it down here and copy just the triangle down. With side lengths 45 degrees, angles 45 degrees and 45 degrees. Side lengths 1 and 1. And now we want to figure out what the hypotenuse is. We'll use the Pythagorean theorem again. We have that c squared, c is the length of the hypotenuse, is equal to 1 squared plus 1 squared. So c squared is equal to 2. 1 squared plus 1 squared is 2. So c is equal to plus or minus the square root of 2. But again, we only want to consider the positive values here. So we have this triangle with side lengths 1, 1, square root of 2, and the interior angles being 45 degrees, and 90. And this, again, is the triangle to memorize. We call this our 45, 45, 90 triangle. And again, we can use it to figure out all of the trigonometric functions of 45 degrees. This triangle is a little easier to memorize than the other one. You just have to remember that the two side lengths are 1 and the hypotenuse is square root of 2. So it's 1, 1, square root of 2. So sine of 45 degrees we can compute by taking, well, in this case we can take either one, of course, but I like to, focus on one just to get in the habit of making sure to identify your angle when you go to compute things. Remember, your trigonometric functions are functions of angles, not of triangles. So you need to specify an angle when you go to compute them. So sine of 45 degrees will be the opposite over the hypotenuse. The length of the opposite side is 1. The length of the hypotenuse is the square root of 2. So sine of 45 degrees is 1 over square root of 2. Similarly, cosine of 45 degrees is 1 over square root of 2. Adjacent side is 1. Hypotenuse is square root of 2. And then tangent of 45 degrees is equal to the ratio of the opposite and adjacent side. So that's 1 over 1, which is just 1. Now, as I said, we will usually be just fine with leaving square roots in denominators, and that's true. And we can leave these sine of 45 values as 1 over square root of 2. However, the book and many resources that you run into will write this as the square root of 2 over 2, which is equivalent. This is what you get when you take 1 over square root of 2 and you multiply by the square root of 2 on the top and bottom. 1 times the square root of 2 is the square root of 2, and the square root of 2 times the square root of 2 is the square root of 4, which gives us the square root of 2 over 2. So many resources that you look at will write sine of 45 degrees, cosine of 45 degrees as the square root of 2 over 2. Personally, I find this overly complicated. I find it much better just to remember sine of 45. I find it much better just to remember the triangle and to use sine of 45 degrees as 1 over square root of 2. However, it's so ubiquitous to use square root of 2 over 2 as sine of 45 or cosine of 45 that I don't want you to be confused when you run into it. So that's what that is. It's just another way of writing 1 over square root of 2. All right, so we can use these trigonometric functions to solve all sorts of problems. So let's look at one. Let's look at an example. A surveyor measures the angle of their vision to the top of a nearby building as 30 degrees. If the height of the building is 60 feet, how far is the surveyor from the building? So this is one, as we often run into, that benefits from sketching out a picture of what's going on. So this is the way I do it. I'd start with the building right here, and then we've got our surveyor who is measuring the angle from a particular position going up to the building right here. And what we're told is that the building has height of 60 feet and that the angle measured between the ground and the view to the top of the building is 30 degrees. Finally, because we're told that this is a height involved. Height is a measurement straight up from the ground, perpendicular, and so we've got a right angle here. And finally, the distances involved are small enough that we're not going to have to take the curvature of the Earth into account. Eventually, we may be dealing with problems like that. You may be dealing with problems that have to take the fact that the ground isn't perfectly flat into account. In fact, some of the largest engineering projects in the world, some of the longest bridges, have to take this into account very, very precisely. There are some very long bridges where the tops of the towers holding it up are a foot apart at their peaks than at their bases because of the curvature of the Earth. But we don't have to worry about that here. This is a small enough problem that we can discount that. So the problem is asking for what's the distance from the surveyor to the building. In other words, what's this distance? As always, when we're working a problem, we want to give names to the unknown quantities that we care about that we're trying to find. So let's call this distance x. We'll say it's x feet. So first of all, we want to say let x be the distance from the surveyor to the building in feet. And now we want to figure out what x is, and here's where the trigonometric functions can help. Excuse me. So when we've got a situation like this, where we've got a triangle and we know some of the information, we know some of the angles, some of the side lengths, and we want to find the others, the trick here is to use a trigonometric function that relates the known information to the unknown information. That is the information that we're trying to find. So in this case, let's note all of the information that we know. We know this angle right here, the angle formed between the ground and the sight line to the top of the building, which is one angle of the triangle that we built. we know one side of the triangle, which is opposite to the 30-degree angle that we're working with here. We know that we're dealing with a right triangle, which is very important. If we weren't dealing with a right triangle, then the trigonometric functions wouldn't apply, at least not directly. We're going to get to that eventually. So these are the unknown quantities, and then the quantity we're trying to, those are the known quantities rather. The unknown quantity that we're trying to find is this x here. And if we look at the triangle and the angle that we know about, this x is the length of the adjacent side. So we look at what we've got. We've got an angle. We know something about the side opposite that angle. We know something about the side adjacent to that angle. And we want to relate those. So we think back to our trigonometric functions. What function relates an angle to its opposite side and its adjacent side? And if you run through them, you'll find that tangent is the one. Cotangent also works, but typically you want to use sine, cosine, or tangent before you use the other ones. Usually, just because they're easier to work with, and because you can plug them into a calculator easier. Most calculators do not have secant, cosecant, or cotangent buttons. So what we can say is that, not sine, but tangent 30 degrees is equal to 60, the length of the opposite side, divided by x, the length of the adjacent side. So this is just using what we know about trigonometric functions. So now we can solve for x. This is just using standard algebra techniques. So we'll multiply both sides of this by x and get x times tangent 30 degrees equals 60. To get x by itself, we'll divide both sides by tangent of 30 degrees. Remember that tangent of 30 degrees or sine of 15 degrees or any of those are just a number, which means you can multiply and divide them away just like any other quantity. So what we get is that x is equal to 60 over tangent of 30 degrees. Now, the question is how far we have to go beyond this. Because 30 degrees is one of our special angles, we know what it is. We know how to calculate tangent of 30 degrees. And so in this case, we'll go and say, well, this is 60 over, and if you look back at the table that we had before, or if you construct the triangle again, here's 30 degrees, we get 1, 2, square root of 3. I see that tangent is 1 over square root of 3. So x is 60 over 1 over square root of 3. To simplify that, we flip and multiply, because that's a complex fraction. So we get 60 times the square root of 3 over 1. And so we get at that's x is equal to 60 times the square root of 3 feet. Now, if this problem as I wrote it is exactly what was given, this is where we would have to stop, because this is the exact height of the building, given the information that we came across. However, most of the time, application problems like this will ask you to approximate the answer. So let's suppose that the problem asked us to approximate this to 2 decimal places. So for this, we could come down here and we could plug in, remember that we want to do all of our approximation at the end. And so in particular, whatever expression you get at the end, you want to put that whole expression into your calculator and do it all at once. So we want 60 times the square root of 3. Whoops. And we see that that's going to equal 103.92. And so I said 2 decimal places. So we want 103.92 feet. And so that's what we would put in. Depending on whether the problem asked us for an approximation or not. If it didn't, we would just answer 60 square root of 3. If it asked us for an approximation, we would give the approximation to however many decimal places were specified.